So yeah, I'm going to be talking about light curve phenomenology and by eye characterization. Already I've not gotten this right. So I'm from Ohio State University. Some of you have probably seen versions of this talk if you saw the other Sagan workshop a couple years ago. So what's the goal of this talk? It's basically just to give you a sort of qualitative, intuitive feel for what microlensing light curves look like, and so in a phenomenological way. So that when you see a microlensing light curve, you can sort of diagnose what you think that light curve is due to. This is useful because it allows you to determine what an observed deviation is due to, whether it's due to microlensing as opposed to some astrophysical or instrumental cause, and in particular if it's due to some potentially interesting cause. For example, planets. I'm not saying only planets are, should probably say e.g., not i.e. Only planets are interesting, but that's a lot of what we focus on, is trying to find planets. And this is useful for a lot of reasons. One is if you're actually doing microlensing follow-up searches real time, which I used to do once upon a time when I used to do science, you can determine whether or not you should try to devote more resources to collecting more data for that particular event. Even after the event is over, you might want to collect more data like AO follow-up, et cetera, which we'll hear about later in the workshop. And then of course we now have so many events that are quote unquote potentially interesting that we have to, and each of them take long enough to analyze that we have to try to prioritize them and decide which ones are the most interesting for analysis. And then finally, we're still not quite, although we're very, very close to the point where we can routinely do thorough parameter space searches for binary lenses. I guess we're basically there, but nevertheless, it's not perfect, and binary solutions have been missed, especially when you include higher order effects like orbital motion. Even as recently as a few years ago, binary solutions have been missed. So it provides, if you can have a guess at what you're looking for, it provides at least some initial conditions for fitting. Although one has to be careful with the degeneracies, which I think Valerio is going to talk about in more detail. Okay, so those are some of the motivations why it's good to have a reasonably good sort of intuitive feel for the phenomenology and ability to characterize perturbations by eye. So why is this even an issue? Right? Well, why is it hard? I mean, you can look at a transit light curve and you can more or less read off the depth and figure out the period and the duration, and that gives you that more or less analytically you can derive the observables from that. But it's not so easy in microlensing, and that's because the canonical parameters that we use to characterize a microlensing event, or sorry, to parameterize a microlensing event, and particularly a binary microlensing event, are not generally directly related, except for some special cases, to the observables. In the case where they are directly related to the observables, you can do basically the same thing as you can with transits, which is you can more or less read off the parameters, and I'm pretty sure there's a workshop, hands-on session to do that for planetary perturbations. But for binaries and more complicated perturbations, you can't do that. So there's no one-to-one relationship between the canonical parameters we use and the observables, and that makes it difficult to just look at the light curve and figure out what those parameters are. So what's ended up happening, or what happened in the early stages of looking for planets and studying binaries with microlensing, was that those of us that were involved in these searches basically looked at thousands of microlensing events with various different parameters, and eventually, you know, in the neural net sense, literally the neural net sense, we developed the connection between those canonical parameters and the observables in our head. Unfortunately, it's, you know, not so easy to download someone's brain and therefore figure out how this neural network works. But you know, if you ask me or Jen Yi or Andy Gould or Dave Bennett or JP or any number of people that have looked at these things, enough of these light curves, at least for binary lenses, we can more or less tell you to a reasonable approximation, unless it's a pretty degenerate case, what the parameters are. And so that's the goal of this, is to try to teach you a little bit about how that neural net works. So I've thought a little bit about how those connections are made, and I'll try to provide some lessons. That's my goal here. Okay, so of course we start with the single lens. Single lens itself has some degeneracies, which I'll actually talk about on Wednesday morning in two limits. One is the high magnification limit, and one is the low magnification limit. The light curves are very degenerate, especially when you consider blending. But anyway, I'm going to give you some general considerations for looking for deviations from the simple single lens form. And the general considerations, there's deviations come in three basic types. One is anomalies, and the likely source of anomalies are more or less finite and understood. At least, like I said, the likely sources of anomalies are finite and understood. And although the phenomenology is exceptionally rich, all microlensing light curves more or less obey general rules. Now, for the binary lens, we basically know what those rules are. For the triple lens, we're in a much more nascent state. So for those of you young people that are interested in getting involved in microlensing, this is a very rich area that you could make some progress in. For triple lenses, we have much less, we've developed much less intuition as to what to expect in triple lens cases, at least in the more complicated forms. I'll show you that some triple lenses can be understood relatively simply as just superposition of binary lens perturbations. And I think this is the most important thing. The word caustic often scares people that haven't encountered it a lot. I'm not actually sure why, maybe just because it sounds evil or something. But if you can understand the caustics of binary lenses, that really helps you. I mean, basically, that's 80% of the way of understanding how binary microlenses should look like. I encourage those of you who really want to become gurus at binary lens microlensing to basically memorize the shape of the caustics as a function of the two parameters that describe them, which is the mass ratio and the projected separation in units of some Einstein ring radius. People typically use the total mass of the lens, but that's not always the best choice. Okay, so we've already seen single lens light curves. And as Rachel said, they're very characteristic. These are sometimes called Paczynski light curves, although I seem to remember he didn't really like them being called that because I don't actually think he's even the first person to show one of these. But anyway, this has a nice analytic form, which basically all of us have memorized. A equals u squared plus 2 over the square root of u squared plus 4, or u times square root of u squared plus 4. And as you go to high magnification, this goes to basically 1 over the separation between the lens and the source. And as if you go to low magnification, as I'll show on Wednesday, it goes to 1 plus 2 over the separation to the 4th power. And so at high magnification, the peak magnification is basically 1 over the minimum impact parameter. And that actually, so you can see here, this is a magnification. This is a u of 0.001. This is a u of 0.01, u min of 0.01, and this is a u min of 0.1. And you can see that it actually works really well, even up to down to magnifications of 10. And actually, it works reasonably well down to magnifications of about roughly 5. So you can more or less read off the impact parameter if it's not blended. That's a very big caveat from the light curve. But anyway, it's smooth, symmetric, timescales from 20, actually you can get down to a few days, of course, if you're looking for very low mass lenses, up to a few hundred days. Magnifications typically observed are 1.5 to 1,000, although we have, of course, gone on either side of this range occasionally. And like I said, in high magnification events, flux is proportional to 1 over time. Okay, so these rules are quote rules. They're not completely 100% rules, but they're reasonably good guidelines, I would say. So generally, well, this is always true. General single lens light curves without higher order effects like parallax are smooth, symmetric, and have no sharp changes as a function of time. So those are very easy to spot, assuming you have reasonable data. Okay, so now we'll talk about anomalies. There are, like I said, a finite number of likely causes of anomalies from the single lens form. The most common is roughly equal mass binaries. The caustic crossings equal mass binaries comprise roughly 10% of all microlensing events so far, although that depends, of course, on the quality and quantity of your data and how high of a magnification event you can detect. There's parallax, which is just due to, in the case of one observer, the orbital motion of the Earth causing an acceleration and therefore a deviation from the rectilinear constant velocity light curve that we or a trajectory that we typically assume. There's, of course, also a satellite and orbital parallax, and I guess Jen is going to talk about all the causes of parallax in various forms. There's finite source effects, so this is just when you get close enough to a region of the lens where the magnification gradient has a second derivative that you can get, you can actually resolve the source, the fact that you're magnifying different parts of the lens differently due to the source being a finite size. This typically occurs for single lenses in high magnification events, but also occurs when you cross caustics or come near to within a few source radii of the caustics. And then a planetary companion, which is one of the things we're most excited about. And then Zalarap, which you might, if you may or may not have heard of it, if you haven't heard of it, it is indeed parallax spelled backwards. And that is because it looks a lot like a parallax. In fact, you can mimic any parallax signal with a Zalarap signal if you choose the right parameters. Exactly, you can mimic it. Okay, so, and then a binary source. And we're worried a lot about binary sources when we first started looking for planets, but they've turned out to be relatively rare for reasons that are somewhat obvious in retrospect, and I can talk about it later if you want. So the sort of first rule of thumb is most perturbations are caused by binary lenses. And binary sources themselves are relatively rare. There's other sources here that I haven't mentioned. You can have, of course, combinations of these, binary source plus binary lens. That's been observed now at least twice, I think, or at least once. You can have, triple lenses or higher order lenses. So I think I counted this right. We have 6 triple lenses that we've observed so far. Someone correct me if I'm wrong. But I was trying to do that math in my head this morning. I think there's 6 times we've seen three bodies as lenses. And then you can have other things as well, but those typically are quite rare. Like in principle, you can have the finite size of the lens be an effect as well. But that's only been observed a few times, and actually not by microlensing survey, but by Kepler. Okay. So rule number 2, finite number of likely causes of light curves of anomalies. The vast majority of these are due to equal mass binary lenses for typical light curves. So generally, you should have the prior that if you see a deviation, it's probably due to a binary lens, although I'll qualify that here in a second. Okay, so what do the light curve anomalies look like? More or less, they come in 3 basic flavors. There are short duration deviations in the wings of the light curve. I'm not going to define wings here precisely, but anyway, not near the peak. There are short duration deviations near the peak. Again, I'm not going to define that precisely, but you'll see, with enough experience, you see what I'm talking about. And then you just have long duration deviations that last a significant fraction of the light curve timescale. Okay, so here are some examples of short duration deviations during the wings. These are 3 different causes. As you can see, they look remarkably similar. You could make them look even more similar if you wanted, but I kind of ran out of patience when I made this slide. But they are due to 3 different effects. So this one is due to a planet, turns out. This one is due to a binary lens, and this one is due to a binary source. Okay, so you can see that they look somewhat similar. But binary sources, like I said, we know subsequently are quite rare. So this is a hypothesis that you should test if you see a short duration deviation during the wings, but it's unlikely to be the right answer. But either of the other two could, in principle, be the right answer, and we have seen various versions of both of these in several cases. Okay? So now you can also have, these are bumps, which is what we're typically used to seeing, but you can also have dips, which I'll show you. If you see a dip in the wing of the light curve, it is a planet. Done. Right? Either that or some really bizarre thing like you've microlensed an eclipsing binary, which is very unusual. But more or less, if you see a dip in the wing, it's a planet. And it's in particular, it's a minor image perturbation planet, which means that the separation between the two lenses is less than the combined total Einstein ring radius. Okay, so short duration deviations of the wings, rule number 3, are likely due to planets and should be monitored or paid attention to or modeled. And in many cases, you can read these off by eye, both for the binary source and for the binary, actually for all 3 cases, the binary source, binary lens, and planet. You can more or less derive the canonical parameters just from the properties of the deviation, at least 2 within a factor of few. And again, one of the exercises is you're going to do that for a planetary perturbation. But keep in mind, you can also have dips. Okay, so deviations near the peak come in 3 basic flavors. One is this sort of rounded in shape, this hump shape. That is a finite source effect due to the fact that you're resolving the source. The second is this double horn shape, and then this looks also sort of like a double horn shape. And so these look somewhat similar to each other. And I'll just do a little, I'll note that there's a little deviation here. It turns out actually there's a planet in this event as well. So just because it looks smooth doesn't necessarily mean that it's consistent with smooth at the level of the quality of the data. So this is a planet, and this turns out to be a close-wide binary. So deviations during the peak can be due to these basic 3 effects. And deviations during the peak are also more likely to show existence of a third body as well. So it's rule number 4. You can have a small caustic, central caustic, or a close and wide binary. And then here are some long duration deviations. These can be caused by a lot of things. Binary lens, parallax, you can see the asymmetry there because I've compared it to a non-parallax light curve. This is a binary source. This is a binary lens. This turns out to be a planet, although you can see that it's a relatively long deviation. So you got to be careful. Just because it's a long deviation does not necessarily mean it's not a planet. And this is a Zalorap. Okay, so long duration deviations are typically not planets, but sometimes they can be. So you have to be a little bit careful. So one thing to keep in mind is how lensing works. Lensing is a mapping. It's a mapping between the source plane and the image plane. And the interesting thing about it is that that mapping can be singular. The magnification is just the area of the images relative to the unlensed area of the source. So the larger the images relative to the source, the higher the magnification. And so a large magnification means a very small patch of the source is mapped to a very large path of the image patch in the image plane. And again, that mapping can be singular, which means for a point source, it is technically infinite. So you're familiar with this because if you try to map a sphere to a plane, you can't do that perfectly. And so a Mercator map projection, in fact, makes it look like things near the pole, where there's an actual singularity in this mapping, become highly magnified, artificially so. And actually, this is technically a fold caustic crossing, which I'll tell you about here in a second. And so for a point lens, what you see is that this is the source. Every single area has the same size, but each part of this source plane gets mapped to 2 places, one inside the Einstein ring and one outside the Einstein ring. And each place where this box gets stretched out into a large area is where you get very high magnification. Okay, and so formally, caustics are the set of source positions where the mapping is singular, or mathematically what they call is catastrophic, and you can get infinite magnification for a point source. Of course, there's no such thing as a point source, so you get large magnification for finite sources. For a single lens, the caustic is a point. It's at the position of the lens. That's the only caustic. For binary lenses, it's more complicated. And so you can understand the phenomenology of light curves largely by examining the caustics. Okay, so I'm just going to go through the caustics of a binary lens. So this is what did I have, 48 minutes? Is that right? Right, okay. Gotta hurry. So here is a equal mass binary, and you can tell that it's an equal mass binary because the caustics are symmetric. And so this is one in which the separation, those are the two lenses you can see here. This is the caustics. The separations are separated by less than their combined Einstein ring radius. And then this is, and so this has this we call this the topology of the caustic. In this case, the topology is such that you have three caustics, these triangular shaped caustics, each of which have three cusps, and then the central caustic, which has four cusps. I'll tell you what cusps and folds. And so these parts here are called folds, and they join at point-shaped things called cusps. And the folds are always concave, and the cusps are always pointy like this in a binary lens with no external shear. Things can get more complicated in other situations, but if you just have point lenses, no smooth source of mass, and no other body that's creating a gravitational shear, then what I just said is always true. There's a critical point, which is 1 over square root of 2 in the total, where the separation is 1 over square root of 2, where you're measuring the Einstein ring radii in the total mass of the lens, where these caustics merge. And then you go to a different topology where you have one single caustic with 6 cusps. And then as you go further increase the separation, you reach the other critical point where you change topologies. That's where the separation is 2 in units of the total angular Einstein ring radius. And then as you keep going, the caustics separate and you get 2 caustics, each of which have 4 cusps, and you can see look very similar to each other. All right, yeah.
Quick question for the initiated. What are the units on?
Einstein ring radii of the total mass. Sorry, I should have said that. Thank you. Okay, so these are the topologies you have. We have the close. We have the separation between intermediate and wide, or sorry, close and intermediate topology, sometimes called the resonant topology when you're talking about planets. Due to a paper by Joachim Wamsgans. This is the separation between the intermediate and wide topology, and this is the wide topology. And no matter the mass ratio, you get all 3 topologies. Okay, so but the shape of where you get these topologies in terms of separation depends on the mass ratio, and the shape of the caustics also depends on the mass ratio. So here's the same case that I just showed for a mass ratio of 1. This is 0.1, so this would be something like if this were a solar mass, this would be at the bottom of the main sequence. You can see that, of course, the caustics become asymmetric. As you imagine, these 2 triangular caustic start to move together, and the place where you get the change in the topology changes. But again, you always get either 3, 1, or 2 caustics, depending on whether you're wide, intermediate, or close. Further decrease the mass ratio, these 2 caustics, the caustics of course shrink, these 2 triangular caustics become closer together, and then the wide topology, you just get this 1 caustic and a very small caustic in the center. So obviously I don't have time to go through all of this in detail, but if you really want to understand microlensing, you should really study these kinds of charts as much as possible, and if possible, if you have a program that can create caustics for you, you should just play around with it. Right, so I said this already, these are the folds, and they meet at cusps. And mathematically, these are different orders of catastrophes or singularities. Okay, so fold caustics have a universal form. As you approach the caustic, the magnification goes as 1 over the square root of the distance to the caustic. Then, of course, finite source effects kick in. As you're resolving the source, and outside the caustic you get much less magnification. And what's going on here is that 2 images are merging as you approach the caustic, and once they cross the caustic they disappear. And then you have a cusp, which is you have magnification going as 1 over distance as you approach the cusp, but outside the cusp, in a very marked difference to a fold, there is still one image that has very high magnification. So what is happening here is you have 3 images that are highly magnified, and when you cross the cusp, 2 of them merge, and you have 1 left over. Okay, so when you pass close to the exterior of a cusp, you get a large magnification. When you pass close to the exterior of a fold, you get basically very little magnification, and you don't know you're about to hit a fold until you do. Okay. So again, caustics, folds and cusps, they have universal forms. Fold caustic crossings come in pairs because they're always closed curves. So if you enter a fold, if you see a fold entrance, there will be a fold exit. If you missed it, that means either you missed your data, or if you see another fold entrance, then you know something really weird is going on because you have a higher order lens. And outside of cusps, you have lobes of high magnification. Okay, so here's the case of a planet, which is what we're, I think, mostly interested. This is a mass ratio of 10 to the minus 3. And then here I have the projected separation in units of the total Einstein ring radius, and the mass of the total, total mass, Einstein ring radius, the total mass, which in this case, because the mass ratio is so small, is more or less the mass of the primary. So this is from here to here is separations less than the Einstein ring radius. From here to here, separations greater than the Einstein ring radius. And so you can see these two triangular caustics, which in the equal mass binary lens were located here, are now located close to the binary lens axis. So here's the star, here's the planet in each case, moving out, as you can see. So here again, two triangular shaped caustics. They get bigger as you get the separation gets closer to 1. Eventually they merge with the central caustic, which itself is also getting bigger. And then eventually they break apart, and then you just get the two caustics, the central caustic, and then this outer, what we call planetary caustic. So we call these the planetary caustic, we call this the central caustic, we call these resonant caustics, and then we call these planetary caustics and this central caustic again. So if you can memorize this chart, you'll go a long way in understanding planetary microlensing. Okay. All right, so here's what the magnification looks like, and this explains why, if you understand what the caustics look like, you'll understand how planetary perturbations look like. So here's the case of a wide typology. Here's your central caustic, and here's your planetary caustic. In these cases, it looks like they're connected, but they're not. It's just that there's this lobe of high magnification that occurs outside of cusps that I mentioned. There's one cusp here, there's one cusp here, and they sort of connect to each other. But you can see that the planetary caustic gives you a very large positive magnification. White here is positive. Large lobes of magnification near the cusps, so the ones on the axis are stronger because that's the shear due to the star. That's that direction. There are small lobes of demagnification, but they're relatively minor on the folds in between the cusps. And if you look at the central caustic, you see this high positive deviation at this pointy part of the cusp. And then you see this negative deviation on the back end of this caustic, and I'll show you a little bit more about that. Then when they merge, you form a resonant caustic. Now this resonant caustic is enormous compared to these other two caustics, but it's also very weak, and you can see that here because you can sort of see that there's a little bit of white there, which is showing you that you actually do get a positive bump when you cross that caustic, but it's not nearly as strong as here. So for most of the resonant caustic, it's very weak. In fact, you can cross a resonant caustic and almost miss it. I'll show you an example of that. But here, the perturbation is very strong. Here, the perturbation is very strong near the cusps, and the demagnification relative to a point lens is also very, very strong. So if you see a strong demagnification near the peak of a light curve, because this resonant caustic is always located near the position of the primary, that's again a smoking gun signal that you've crossed a resonant caustic of a planetary lens. Then, of course, as the separation gets smaller, these caustics separate. You get these two triangular shaped caustics, which themselves are very strong, but actually quite small. But again, you get this very strong lobe of demagnification. What's actually going on here is you're effectively destroying one of the two images. As Rachel talked about, you form two images. You're destroying one of the two images, the minor image of or the image inside the Einstein ring. And so basically the only magnification you're getting is due to the image outside the Einstein ring. You still get this negative deviation here as well. Now, you might look at this and say, hey, those look kind of similar to each other. And in fact, they do. Mathematically, as Q approaches 0, they're identical. This is called close wide degeneracy. Okay, so that's close, resonant, and wide. All right, so planetary caustics, S greater than 1, positive deviation, bump, typically on the wings of a light curve. This is the planetary caustic. This is the central caustic. If you look at the scales here, the central caustic is always smaller than the planetary caustic. Okay, and it actually gets smaller relative to the planetary caustic, the smaller the mass ratio you get. Okay? So these perturbations are annoying because they can happen anywhere at any time and they're unpredictable, which means you have to monitor the entire light curve continuously. But they are actually larger. There are more planetary caustics happening, deviations happening in the universe, not that we're observing them necessarily, than central caustics because the caustic is bigger. And so the size of the caustic is proportional to the mass ratio to the 1/2 and the separation to the -2. So as the separation gets larger, the caustic shrinks. As the mass ratio decreases, the caustic shrinks. For S less than 1, again, you get these two triangular-shaped caustics. If you pass between them, you get this demagnification trough. If you pass on one of these caustics, which you can see are quite small, then you'll get a positive deviation, and we've seen that. But typically what you see is this negative deviation. And you can see this planetary caustic. The central caustic, again, is very small, but should look, to your eyes, quite similar, except the mirror image of the other caustic, and that's due to this degeneracy that I talked about. The size of these caustics here, they actually shrink as mass ratio to the 1/2, the separation cubed instead of separation squared. And as S approach 1, this deviation, negative deviation, gets bigger. So how much time do I have? 20 minutes? Okay, good. I'm doing fine then. I don't think I need to, but it should be all right. I'll slow down a little bit because I know this is new to some people. I'm probably going pretty fast. All right, so back to the central caustic deviation. Sorry. So, okay, so just to recap, since I have a little time. If you're going to detect the planetary caustic, typically you'll detect it on the wings of the light curve. It's typically unpredictable, so you have to sort of monitor the entire light curve, and that's a pain. It's very resource intensive. But now that we have surveys that have large enough field of view that they can do this, we are able to do this, like KMTNet and MOA and OGLE can all do this now, and have detected planets sort of serendipitously this way. If you see this trough, this you know almost immediately has to be a planet. There's a mild degeneracy with parallax, which I won't go into, but more or less, if it's a strong negative trough, it's a planet. And then if it's a positive deviation on the wings, it's like I said, it's a planetary caustic or binary lens caustic, because in principle you could be hitting one of those triangular caustics of the binary lens as well. And again, it's unpredictable. Okay. So, here's this S1/S degeneracy. This also exists in binary lenses. And this is for the central caustic. Obviously, the planetary caustics look very, very different, as you'll see, right? In the S less than 1 case, there's 2 of them, and the demagnification trough in the middle. But the central caustic looks very, very similar, and as the mass ratio decreases, this degeneracy becomes essentially perfect. So you can't tell the difference between S and 1/S. Also, as S becomes large or small, the degeneracy becomes better as well, which means that if you're able to detect a caustic due to an S of 0.3, you can't tell if it's S of 0.3 due to a central caustic. You can't tell if it's S of 0.3 or S of 3, or S of 0.33 or S of 3. So just to show that here's that central caustic, and then here's the central caustic. What am I doing here? Oh, I'm sorry. I'm doing central. Oh, right. Yeah, that's what I'm doing. Sorry. So here's S less than 1. Here's S greater than 1, where S is equal to 1/S in both cases. And you can see the central caustic is more or less identical, even though the 2 planetary caustics are very different. And the perturbation that you get is essentially identical, even though the planetary caustics, the planetary caustics look very different. And the S's are obviously radically different. Okay. So now just to explore a little bit more what kind of perturbations you get from the central caustic, if you pass this back end, that's when you get this double-horned profile, and we've seen this in a number of events. If you pass the front end, you get a bump. Now, if you pass parallel to the caustic, the central caustic, you don't really get very much unless you're really close to the caustic. Okay, you can get this slight deviation, but it's not very much. And that's because not much is happening here in terms of relative fractional deviation. There's some deviation here and some deviation here, but if you don't get very close to those lobes of magnification, excess magnification near the cusps, then you won't see very much. And then, of course, if you look at the this caustic of a binary lens, this in case can be either a close or wide binary lens. If you pass along this way, you can also get a double horn shape, which looks remarkably similar to the planetary caustic in the back end. So this leads to a sort of, it's not a well, it's not, maybe it is a mathematical degeneracy, I can't remember. Anyone know? Is it a mathematical degeneracy, Dave? Or is it just an accidental degeneracy? I think it's accidental, yeah. So you can get double horn peaks due to either a planet or a binary. And the difference the reason fundamentally why you're getting this is that in this case there is a cusp right here, which should give you a triple horned or triple peaked, but this cusp is extremely weak. And so unless you're passing very close, it's very hard to see it. So if you have relatively poorly sampled or poor accuracy data, you can confuse a binary lens or a planetary back-end central caustic deviation with each other, although you can see the degeneracy is not exact. Okay, so planetary and wide close binary perturbations at the peak can be distinguished by the precise morphology of the deviation. All right, finally, resonant caustics are fascinating for lots of reasons. The first planetary event was detected on Earth as a resonant caustic, barely. And so again, it's a single caustic with 6 cusps. 1, 2, 3, 4, 5. Wait, where's 6? Well, there's one right in the middle there. Can't really see it. So they're big, right? That means that they're in principle the easiest to detect. I didn't mention this before. Bad me. The planetary caustic size scales is Q. Remember the central caustic size scales is Q. So whereas the planetary caustic scales as Q to the 1/2, right? So that means that as Q goes down, the central caustic size relative to the planetary caustic size decreases more rapidly. Okay. So, it's easier in some sense to detect planets due to a small mass ratio of planets due to planetary caustics, assuming you can get continuous light curve coverage and resolve the source, which is not always guaranteed. All right, now back to resonant caustics. Now, resonant caustic scale is Q to the 1/3, which is even weaker than either of the other two. So that means that resonant caustics are always bigger than the other two, and they're always bigger at any mass ratio. So they're quite large. They have a large cross-section, and so that means typically they're very easy to detect. We've detected many resonant caustic events. But like I said, they're also very weak. The caustic perturbation can be washed out relatively easily. So these cusps are this cusp is reasonably strong. These are weaker. These cusps are strong. There's a lobe of demagnification here that's reasonably strong, but these folds here, so in this one, are exceptionally weak. And you can sort of naively, it's not really precise, you can think of it as you've taken this caustic and you've stretched it out, and as a result, it's very weak. That's not a precise mathematical statement, but that's the way I think of it. So you can see that here this is a caustic crossing. Again, if for a point source, they're all formally infinite, so they're all strong in that sense. But if you add finite source effects, this gets damped down a lot. And in particular, so does this one. So these is a single lens. This is with finite source effects. And so you can see in particular this caustic crossing, barely you can even tell was a caustic crossing. I'll show you a real world example of that where the caustic crossing was actually missed in real time because it was so weak. Okay, so the other very fascinating thing about resonant caustics is their precise shape depends extremely sensitive to exactly what the separation is. So here's a mass ratio of 10 to the minus 3, so roughly Jupiter to the Sun. Separations in units of the total Einstein ring radius of the Einstein ring radius of the total mass between 0.9 and 0.19. So this is just 30% difference here. And you can see that the shape of the caustic changes dramatically as a function of S. What does that mean? Well, that means that your light curve morphology is going to depend very sensitively on S. But really interestingly, that means that orbital motion of the planet for resonant caustics can have an enormous effect. So even small changes in S can lead to large changes in the morphology. And so small changes in the orbit of the planet, of the position of the planet relative to the star in separation can cause large deviations. And I'll show you an example of that. This is something that we sort of learned empirically, or at least I learned empirically by the first two-lens microlensing event. Okay, so perturbations from resonant caustics are generally weak, long-lasting, and can show these characteristic demagnification troughs. All right, so that's the end of my tutorial. If there's stuff you want me to, since I have extra time, if there's stuff you want me to go through more carefully, I can. But I just thought I would go through and do some examples now that I've taught you the rules, quote-unquote rules, and see if you can come up with some answers. Okay, so here's observed event number 1. Who says this is a single lens? Yeah, see, you guys have already learned something. All right, who thinks this is a binary? Who thinks this is a planet? All right, good. You think it's a planet. Tell me what caustic this is due to. Planetary, resonant, or central? Okay. Either of those are reasonable answers because it could actually be either one. And which part of the caustic is it passing? Let's say it's a central caustic, which it turns out to be. Which part of the caustic is it passing? Is it passing the pointy front end? Is it passing the back end? Or is it passing parallel? Who says pointy front end? Who says parallel? Who says back end? See? You guys are almost done. You didn't even go to the rest of the Sagan workshop. All right. Here's another example. Who says this is a single lens? All right, I'm not going to ask that anymore. Who says this is a binary? I got one binary. Who says it's a planet? The rest of you just aren't sure? I mean, or you think it's something else? All right. Look at that. Look at that. Who just isn't sure? And what two things are you thinking it might be? All right, let's go back to our rules. Planetary and wide close perturbations at the peak can be distinguished from the precise profile of the deviation. So if you see this double horn profile, either it's a binary, close or wide, or it's a planet. Okay? So this in principle could have been a binary. Turns out that you can see right here this little extra bump that tells you that there's a caustic in the middle, a cusp in the middle, which means it's a planet. Okay? In this case, you don't see anything. Now, that doesn't automatically tell you it's not a planet because you could be pretty far away from that cusp in the middle, right? But you can tell that it's either a close wide binary or it's a planet. In this case, it turns out to be a planet. Okay? Now, so it's a double horn profile. So you know it has to be either a central caustic passing by the back end of the central caustic, where it has two cusps and the small cusp in the middle, or a binary, one of the, what is the word? Asteroid binary, force binary, where you're passing sort of a 45-degree angle. So in this case, detailed modeling tells you that it's a planet. And you're pretty far away from that central, that middle cusp. But if you look closely at the deviations here, you get some significant deviations. Now that is another rule which I haven't tell you, which is that if you have a third body in your system, then that third body typically reveals itself near the peak of an event when you're closest to the primary. All right, so let's go back to our caustics. Let's go back to a central caustic. The primary, which I should have noted, is, I told you before, is always at 0, 0 in this plots. So this is the primary. So if I had a third body in this system, it would distort this caustic right near that primary. So the best place to look for third bodies is when you get the closest to where the primary lens is. And that's, in the case of when you pass one of these double horn caustics, is always right there in the middle. So when we first saw this event and Subo Dong was modeling it, this one here, I took a look at this on his curve and I said, there's a third body in this system. And in fact, it turns out that that's true. This is the first circumbinary planet ever discovered by microlensing. Bennett et al. 2016. Is that right? Dave? What, 2017? No. This was when the event was discovered. It took us 10 years to figure out. Oh, there it is, right. Sorry. Okay, oh, look how good I was. I actually cited people. Oh, good for me. All right, here's another one. Obviously not a single lens event. Who says it's a planet? Who says it's a binary? All right. Why do you think it's a binary versus a planet? Or are you just guessing? So this is a tough one, actually. We weren't sure when we first saw this whether or not it was a planet or a binary, but it turns out to be a binary. Typically, you can't get this kind of large asymmetric double horn shape in a planet. It's pretty tough. But again, it's the same principle. If you see a deviation near the peak and it's got this double horn shape, it's not always easy to tell by eye whether or not it's a planet or going in the back end of a central caustic or whether or not you're going 45 degrees from a closer wide binary caustic. This one's a tough one. Binary? Who says binary? I got one binary. Who says planet? All right, yeah, there's one clue here that tells you that there's, okay, so if it's a planet, what is the caustic? It's either planetary, central, or resonant. Who says planetary? Who says central? Who says resonant? All right, good job. It's a resonant caustic, indeed. Actually, we haven't yet to find a good model for this event, despite... No, I haven't. But what I wanted to point out is, see this little thing here? Right? That's an extremely weak caustic entrance, right? And I remember I told you weak caustic entrances are a signal of resonant caustics. See this here? This is a lobe of demagnification. Again, a signal of a resonant caustic, okay? Also turns out that there's another perturbation somewhere over, caustic entrance somewhere over here, which we don't really understand yet. There are some models for that, but they don't fit this data very well, and they aren't exactly physical. Maybe Dave can tell you about that. All right, here's one which actually I got wrong the first time I looked at it. Binary? Planet? Could be a binary or a planet. So this is the first planet discovered by microlensing, and it turns out it crossed a resonant caustic. And it also crossed the resonant caustic in two areas where it was strong, and it lasted a significant fraction of the event. So I thought this was a binary the first time I saw it, but no, it's indeed a Jupiter mass ratio planet, discovered by Ogle and Moa. Okay, this one. Remember, I gave you a very, very clear rule on this one. What is it? Come on. Planet. No question. You know how many years we waited to see a light curve like that? We'd been plotting light curves like this for like, I don't know, when was this discovered? For a long time, 15 years, I guess. Well, no, 6 years. Well, no, 15 years. And then finally we saw this beautiful, beautiful demagnification trough with these two bumps where you're passing close to the triangular caustics. Okay, almost done. This one. This one was on the door of my wall. Now, probably everyone's seen this one already, so it's not very hard to figure out. But this one was sitting on the door of my wall, door of my office at the CFA for 2 years, while I stared at it trying to understand what the hell was going on. So there's this short timescale deviation here, which you might think is due to either a binary passing one of those triangular caustics, or maybe a planetary caustic. Turns out to be neither in this case, so my rules are not really rules, they're just guidelines. Turns out there's a caustic crossing here, which we missed in real time due to MOA. I don't know, maybe Dave noticed it in real time. I didn't have the data, and I wouldn't have noticed it anyway. But you can tell it's very weak. Wait, that should give you a clue, right? Very weak. And then there's this very strong caustic crossing here, and then there's this drop, very sharp drop. And in fact, my original model predicted that it should keep dropping, which it didn't. It rose again, and then dropped, and then peaked again. So overall, this morphology should tell you that this is a resonant caustic, and indeed, basically true. But that there's extra little feature here that's not supposed to be there. But where it is exactly where I told you that if there's a third body in the system, that's where you should look. So eventually, I got my senses together and showed Dave a topology, which he ended up was able to fit, which is, oh my God, I'm not even going to show the caustics. Anyway, turns out this is mostly due to a Saturn mass planet, but this perturbation is due to a Jupiter mass planet that's further away. So this is the resonant caustic of a Saturn mass planet. 1, 2, it's crossing one part of the resonant caustic, crossing the weak part of the resonant caustic, exits the very strong part of the resonant caustic near the magnification trough, and then it hits the caustic very tip again. And the reason why I had a hard time modeling this, Dave was able to model it, was because my model didn't include orbital motion. And this is a resonant caustic, which I said is very sensitive to the precise shape. So if you don't have orbital motion, then if you cross 2, 3, and 5, you miss 1. So the caustic shape changed enough between here and here that you actually hit another part of the caustic. And then you have this Jupiter mass perturbation, which is essentially due to the central caustic of a Jupiter mass planet that has a separation greater than 1. And so Dave was eventually able to find a orbital motion plus parallax plus finite source effect 3-body lens model. And so this is a Jupiter-Saturn analog. And here's that entrance that you can see is exceptionally weak. Okay. The nice thing about triple lenses is in many cases, you can just model them as simple superpositions of the light curves due to a binary lens. So here's this is basically what my original model predicted. This is the Saturn mass perturbation due to the central caustic. It has all the hallmarks of a central caustic, demagnification trough, weak caustic entrance. This would be what happened if you just had the Jupiter. You're passing the front end of the central caustic, so you get a bump. And if you add this plus a single lens, and would divide by, or subtract a single lens, then you get this gray curve, which you can see matches very closely to the exact triple lens solution of the black curve. So one of the nice things about triple lenses is that they're more or less, triple lenses of small mass ratio companions, so in other words, planetary systems, they're more or less perturbations that more or less add perturbatively. It's not perfect, as you can see, and there's some situations where it can be pretty bad, but for the most part, they add perturbatively. And last one, classic. Anyone? What? This is a hands-on session. What? Oh, right. Yeah, I probably should have noticed that. Anyway, is this a hands-on session one? Oh, okay. Anyway, you can read off you can read off, well, there will be something similar to this, I assume, right? No? Anyway, you can read off the parameters of this perturbation basically with simple geometry. So, and with that, I'll stop. Take any questions.
Okay, question for Scott.
Oh, I should show this though. See this little this curve right here? This dash thing that doesn't fit the data at all? That's the best binary source fit, which you can see doesn't fit very well in this case. Well, not. So at some point you start to reach the limit of geometric optics, and so the two images start to, so your source size becomes so small that your two images start to interfere with each other, and so that actually sets the limit to the maximum magnification you can get. No, you can't theoretically get infinite magnification, which is good because that would violate some conservation laws, I think. Maximum magnification we've ever seen, 3,000. I think that was the paper, that was the event that Jen analyzed that found, no? Or was that the terrestrial planet? Oh, Subo's one, yeah. So we've seen several that are over 1,000, and one that actually exhibited terrestrial parallax because the magnification was so large. In other words, the event looked different on one side of the Earth than the other side of the Earth. Yeah.
So you mentioned that you were initially worried about binary sources, but then in retrospect,
Yeah.
it's obvious why does it matter, and they're rare. Can you, it's not always
It's not obvious, but parts of it are not obvious. One thing is that unless you pass close to the second source, it just exhibits the main effect the second source has is to add unmagnified or very weakly magnified blended light, which we always see blending in ground-based light curves. So we can't tell that it's due to a bound source or just due to some unrelated source, unless we get adaptive optics imaging and some other things. The other thing is that if you ask what fraction the other two things are, if you ask what fraction of binary stars have separations within a factor of several of the Einstein ring radius, just using the usual Duquesnoy-Mayor or Raghavan mass ratio separation distribution, it's not that many, right? Because the binary for solar type lenses, the binary distribution function peaks at 10,000 days, I think. So the very close binaries are relatively rare. The other thing, which should have been obvious in retrospect, is that the mass ratio distribution of binary lenses is more or less consistent with being flat. And the mass luminosity relation goes as mass to the 4.5-ish, and for solar type lenses, it's slightly weaker for when you get below the fully convective boundary. So that means that unless you're basically equal mass or very close to equal mass, the second star is extremely faint compared to the primary star, which means you have to pass exceptionally close to it to see it, and that's a priori very unlikely. That's the basic reason. Nevertheless, we have seen several binary source events, and we've actually seen one binary source binary lens event. One? Right? Two? Yeah. But we haven't seen more than one yet, right? Maybe.
Maybe 270 is a binary source.
Oh, that's right. That's possible. Right. 270 is the one that I showed that has we have yet to find a satisfactory model. Okay.
Other questions? Right. If not, let's thank Scott.
You're next.